Hi everyone, welcome back to Math 111. This is Scott. Let's get started. What we're going to do today is finish up 5.2 and then also cover 5.3. So 5.2 continued. So when we last looked at 5.2, we looked at the formulas of functions, of polynomial functions, and we were able to, from them, figure out what the end behavior would be. Also, to figure out what the intercepts would be. Now, we can also do that if we have a graph. So, for example, given a graph, we can tell its intercepts and end behavior visually. Now, the way this is going to look in the book is that you will be given specifically a function such as this. F of x is equal to -2 times x plus 1 squared times x minus 2 times something like x squared minus 9. Something like that. So this is maybe a little bit bigger than you would typically see, but there's no harm in it because we are not going to be doing anything by hand. We're going to be doing it graphically. And then we can use Desmos to get information about its graph. And now I'm going to switch the camera so we can do just that. Alright, now to graph a function such as the one we just wrote on a graphical software such as Desmos, we just have to find a browser, or you can download the Desmos app for your phone, and you just click start typing Desmos, and then you start clicking the first things that come up, and you'll eventually be there. So here I am in Desmos, ready to go. So here I want just move that a little bit out of the way. So what I want to do is graph f of x equals -2 times x plus 1 squared times, got to move out of the exponent if you are typing this, x minus 2, oops, and then times x squared minus 9. Now, when you look at this, you can see that you can see the information. You can actually see it a little bit better if you switch it to projector mode and maybe get rid of the grid. You don't need that for this. And then you go to the settings here, and we might that's fine actually. So I might have wanted the grid for finding those intercepts, but this should be good enough. Okay, so the information here is good enough as is to tell me the x-intercepts, and then I can zoom and scroll and do all kinds of other things to figure out the y-intercept. So right now it's a little hard to tell, but I can just zoom around until I find it, and then you click it, and if it's the point, then it'll tell you. Okay, so I can tell what I need to tell from this, so I can zoom out a bit. I got that point already identified. Oop, it's a little bit far. So I need to know about the end behavior, and I need to know the intercepts. So here I know the end behavior. Actually, the best thing to do in this case, this is a situation where we can tell that all the action is happening easily within the -5 to 5 on the x range. So it's easier if we customize it to make that happen. -5 to 5, you can set the boundaries for the x and y separately, and then for the y-axis, I'll go negative. It was 36 we could see for that y-intercept, so I'm gonna go -50, and then over here I'll make this one, let's say 50. So it gives us a nice smooth, easy to read graph. And then on Desmos, you can find the values of these intercepts by just clicking on them, and it will tell you. So we can see all the intercepts, and we can furthermore see the end behavior. It is going up on the left, it is going down on the right. So that's what we can tell from the graph. Okay, now that we're back to this view, what we should do in order to record our progress is sketch a graph such as what it looked like on Desmos. And the important things to note about it, so at this point there was, this point was -3, 0. There was an intercept. There was another intercept at -1, 0. This one is a little bit special for reasons we'll see in the next section. -1, 0. Down here, it's -30 or 0, -36. Then over here we had 2, 0. Then we had 3, 0. And then the way it looked was it came down, went up, went down to that point, came up, and then came up and then back down, and went like that. So that's enough information for us to state the facts, such as we asked ourselves before about these. So the intercepts, we can now state that there is a y-intercept at 0, -36, that's where it crosses the y-axis. And then there are x-intercepts at -3, 0, -1, 0, 2, 0, and 3, 0. We could have found all that out also algebraically, taking the factors one by one and setting them equal to 0, but we can also just use the graph. And then for the end behavior, so that's the behavior as we go to the left or go to the right. So as we go to the left, we can see that it is going up. So that means that f of x is going upwards, that means to positive infinity, as x goes left, that's negative infinity. So this is left, up. This is up, this is left. So up as it goes left. And furthermore, we can tell that f of x goes to, so that's now this arrow down here. So this is going to be right and down. So we can state that as f of x goes to negative infinity, that's the down part, as x goes to positive infinity, that's the right part. Now, lastly, in 5.2, so this is what we'll do for all all similar questions in 5.2 where you are going to be given a formula and asked to tell about the intercepts and the end behavior. And now the last task of section 5.2 that we're going to cover is you will be given some information that will enable you to make a graph and or to make a polynomial, and then you'll have to reverse engineer what we did earlier in order to construct a polynomial such as the following. So example, let's say we have, so find a formula for a polynomial of degree 2 with y-intercept 0, 4 and x-intercepts -1, 0 and 4, 0 such that f of x approaches -infinity as x approaches -infinity, and f of x approaches -infinity as x approaches infinity. Okay, so there's the task. So what we've got here is end behavior, x-intercepts, a y-intercept, an overall degree. And we need to make a polynomial that makes all this happen. Well, before anything else, it can be helpful to just kind of sketch what we are talking about here. So here's what it would look like if it had x-intercepts of -1, 0 and 4, 0. Here's what it would look like if it had a y-intercept of +4. Now because this is, which is down, as this, which is left, that means we're going to have an arrow, it's going to be generally going that way. And then here we've got again down, and we've got here right, that means we're going to have an arrow going generally that way. So those are just two arrows to help guide us. And now let's think about how this is going to go. So it's got to go up, and because it's a polynomial, in fact it's a parabola, it's got to have a nice kind of smooth arc to it. No overly abrupt changes, no corners, no gaps, no vertical asymptotes, no horizontal asymptotes, nothing like that. Just a nice smooth arc to it. Should look like that. Now because of the end behavior, we know that it's going to have a negative leading coefficient, because it looks like a downwards square. But let's figure out what we need to figure out here. So first off, the x-intercept of -1, 0. So that means that x equals -1 is going to be one of the places that's going to make the whole thing equal to 0. Now if we add 1 to both sides, it's going to give us x plus 1 equals 0. So this will be one factor. Also, what we could have is 4, 0, which, going kind of backwards of the stream that we went through before to reason these things out, means x equals 4, which means x minus 4 equals 0, which means that's a factor. So we got a factor and another factor. Now f of x is equal to, now we have a factor x plus 1, we have a factor x minus 4. Now if we needed to, we could add exponents to these that wouldn't change whether they were factors or not. And so we could put a square or a cube or what have you there. And the reason we would need to do this is to make the degree match what we were told. But here we were already told a degree of 2, so that's what we would get here. This would multiply out to make an x squared. So it's all pretty good except one thing. As noted right here, we're supposed to have an end behavior that is pointing down on the left and down on the right. This one, if we were to figure out the leading term, would be positive x squared, which is going to end up with an upward facing parabola. So we need to put a negative in here, and this is to match the end behavior. If it weren't for that end behavior, what we had without the negative would have been good enough. But because of it, we need to make that little extra change. Now we didn't use in this the y-intercept at all, actually, because it was actually the y-intercept that we would have gotten if we were to plug in x equals 0 into this. But in the next section, in 5.3, we'll see what to do if we are going to have to get a little bit extra creative on what goes in front here. But that's coming right up. So now, in section 5.3, we're going to discuss graphs of polynomials. We're going to discuss them in more detail. So graphs of polynomial functions. So first off, let's just state our goals here. Our goals. Produce a graph by hand for a polynomial based on its formula, or vice versa. Produce the formula for a polynomial based on its graph. Now, one of the most important things that we're going to have to do here is produce polynomials in what is called factored form. So, factored form. The idea here is if you have a polynomial and it is given to you as a bunch of terms, you will need to put it into the form that is factored as much as possible. So use the techniques of factoring put a polynomial into factored form. From factored form, we can find the X-Intercepts. Or T-intercepts if the function is written with a T. Or T-intercepts. Depending on how the formula is written. Now, here are some of the techniques that we'll need to use. Techniques. So we might need to do what is called factoring by grouping. So we'll see some examples of this in a second. I just want to put the names of these down into the record so that way if you have to look them up at some point on the internet, you can do so. So we've got factoring by grouping. This is going to be one of our common techniques that we're going to use. Another technique that we are going to be using is going to be taking higher degree polynomials that act like quadratics. And the way we say this is we say something like it is quadratic in x cubed, for example. And then other things that are going to happen is sometimes you just pull out a common factor first, and then that makes everything easy. So, oops, sorry, I lost the camera there. So, pulling out common factors. And then another important technique that we will have to sometimes employ is what's called perfect square polynomials, where it's not actually it doesn't look like a perfect square. Sorry, not perfect square. I mean difference of squares. Difference of square. Difference of square polynomials with square roots. Okay, now we'll see examples of all of these as we progress. But let's try our luck. So find the x or t-intercepts of the following. And for our first example, let's just take on something relatively straightforward. Let's say a of t is equal to. So it's already going to be in factored form, and so there's not going to be a whole lot of crazy stuff that we have to do here. We could have 2 times t minus 3 times t plus 4 times t minus 8. So what we have here is already in factored form, so we don't have to worry about it too much, but what we can do is just take the 3 factors, ignore any factors that don't have a t in it, set them equal to 0 separately and see what you get. So t minus 3 equals 0 means that t would equal 3. That would just be adding 3 to both sides. T plus 4 equals 0 would mean t equals negative 4. That would just be subtracting 4 from both sides. T minus 8 equals 0 means that t would equal 8. And that would be just adding 8 to both sides. So those each give us the x-intercepts of 3, 0, negative 4, 0. Sorry, these are t-intercepts, not x-intercepts. Not that it matters in the final answer. And then 8, 0. And you can separate your intercepts with semicolons or just commas, whatever you think looks clearer. Alright, so there's that. Now, let's try an example that requires some factoring by grouping. So let's say what we had was something like this. G of x is equal to, and then we'll say what we have is something like 3x cubed minus 2x minus 2x squared minus 6x and then plus 4. So the way this works is you take the expressions that you see and you set them together in two pairs of groups. And for the ones that we're going to be looking at, it'll typically be the case that you can just go with the first two and the last two. Usually, when you're doing these kinds of things, it will work in almost any order except possibly one. So then, what you want to do is you want to take each pair, and you want to pull out a common factor that you can get from each of these pairs, so that when you pull out the common factor, what's left behind will line up with what is left behind in the second one. So here, the common factor that they both share is an x squared. And if you pull that out, that's going to leave a 3x minus 2. Now the goal here is to pull out whatever you can so that this will also leave behind a 3x minus 2. Both leave the same factor behind. So here, if you look at this, this has as a common factor 2, nothing else. And then there's an x and, 3x and a 2. Now, if I wanted this to match this, that would have to be minus, this one would have to be plus, which is the opposite of what we had before. So we pull out not a 2, but a negative 2. And the reason for that is that what we end up with right here is going to be the same as what we ended up with right here. So this should match this. And if it does match that, then what you do is you put that off to the side, minus 2, and then you basically factor out that common factor, and then what's left here is an x squared minus 2. So once again, you took them by pairs. You factored out the common factor from the first pair, and then you looked at what you needed to pull out from the second pair to make what was left behind match. And that would be a negative 2. So then you'd leave behind a 3x minus 2 in both cases. And then what that leaves you is an x squared times a 3x minus 2 and a negative 2 times a 3x minus 2. So you can pull out the 3x minus 2 from both cases, and that leaves behind an x squared minus 2. Now, this part right here actually is a case of something that can be broken down into two factors, it's technically a difference of squares, where this is the square root of 2 squared. So what that means is what we have is x plus square root of 2, x minus square root of 2. And then that times 3x minus 2. And then that gives us the opportunity to now look at the three pieces separately and look at what intercepts they would give us. So x plus root 2 equals 0. That gives us x equals negative root 2. X minus root 2 equals 0. That gives us x equals root 2. Adding to both sides, 3x minus 2 equals 0. That gives us 3x equals 2, which gives us x equals 2 divided by 3. So then that gives us the three x-intercepts of negative square root of 2 comma 0, square root of 2 comma 0, and then lastly 2/3 comma 0. All right, now if we were to take on one of the other examples, so another example would be something that has common factors that can be pulled out. So something that looks like that might be along the lines of, so this is example C. Let's go h of t is equal to t to the 5th minus 2t to the 4th. Just something like that. So this is not so hard. Well, the common factor that they share is t to the 4th. And then that's going to leave us just a t minus a 2. Now you take them each separately, set them equal to 0. T to the 4th equals 0 means t equals 0. T minus 2 equals 0 means t equals 2. And then you turn each of these into a point to make the intercept, the t-intercepts in this case. It's going to be 0, comma 0 and 2, comma 0. And then the last of the kind of unusual cases that we will see will be something along the lines of this. So let's say we have something like g of x is equal to x to the 6th minus 4x to the 4th minus 5x squared. So here, once again, we have a common factor that we can pull out of everything, such as x squared. And that leaves behind x to the 4th minus 4x squared minus 5. Now, when we pull this out, then that's going to leave us with this expression here, which is not exactly factorable in a usual sense, except that we can think of this as being this is basically now quadratic in x squared. That's how you word that. And what that means is, what we have is a constant, we have an x squared, and we have an x squared squared. So in a way, it's almost like we have like a new variable, y, which is equal to x squared. And this actually then factors the same way you would if this was just like y squared minus y, and then a constant. And you can just actually now factor it as x squared, x squared. Now we're going to have, we need two numbers that multiply together to make -5, add together to make -4. So that's going to be a -5 and a +1. And if you look at this and you were to FOIL it all out, you would end up with x squared is x to the fourth plus x squared minus 5x squared minus 5. So that part would all line up with that. Now, here we would have again the same breakdown as we had before. So it's going to be x plus root 5, x minus root 5. And over here, this can't be factored. And the reason is because we have over here a sum of two squares, and there's no way of making the middle terms disappear in that case. If it's a difference of two squares, then when you FOIL it all out, the middle terms cancel each other out. But if it's a sum of two squares, that doesn't work. So then, what we have here is x squared equals 0, which leads to an x equals 0. What we have here is x plus root 5 equals 0, which leads to x equals negative root 5. What you have here is x minus root 5 equals 0, which means x equals root 5. What you have over here is x squared plus 1 equals 0, which if we could solve that, we would have to do something like minus 1. So x squared equals -1, but this is impossible. So there's no solution from that factor. The other factors, though, do give us solutions. So we have 0, 0. We have -5, or negative root 5, 0. We have root 5, 0. And that's all. That one gave us no new factors. Now there's an important thing that we have to also take into account when it comes to these particular expressions, and that's that sometimes we had an x squared which equals 0, and in a way it equals 0 twice, and then other times we only had the thing to a power of 1. So what that refers to is the multiplicity. So zeros and multiplicity. So zero and multiplicity has to do with some of the features of a polynomial. So first off is 0. Of a polynomial. So this is an x value. This is the x value where it equals 0. So in other words, it's the x value of an x-intercept. then the multiplicity of a 0 this is the exponent outside the factor. That produces the 0. So as an example, you have f of x equals x minus 1 times x plus 1 squared times x plus 2 cubed. Let's say you had something like that. Then the values that make each of these factors 0 would be the zeros of the polynomial, and the exponents up here would be the multiplicity of the 0. So zeros. Well, we'd have x minus 1 equals 0, which means x equals 1. And the multiplicity, we'd have here x plus 1 squared equals 0, which means that x, so take the square root of both sides, basically x plus 1 has to equal 0, which means that x equals negative 1, and the multiplicity here is 2 because it was a square root, or because it was squared. Here we'll have x plus 2 cubed equals 0, means x plus 2 has to equal 0, which means x equals negative 2, but here the multiplicity will be 3, and the reason is because it was cubed. Now the reason for the multiplicities being the exponents out here is that those exponents will determine the nature of the 0. So I should say multiplicities. Say note. Multiplicities tell us the behavior of a polynomial at a0. So we always know that the 0 is going to be the location of an x-intercept, but what we don't know is exactly what kind of x-intercept it's going to be. Will it pass right on through? Will it bounce right off? Will it wiggle through? So multiplicity 1. So this means that this has degree 1, which means it passes through like a line. So it passes through the x-axis in a way like a line. Like a line would. So it goes straight up through, or it goes straight down through. Multiplicity 1 means it behaves the way a line would. Multiplicity 2, on the other hand, this means it bounces off the x-axis like a parabola would. So multiplicity 2 means that when it gets to the x-axis, it forms like a little parabola shaped bounce. or maybe like that. So in other words, it acts like a degree 2 polynomial. Multiplicity 3. So here, what this one does is it wiggles through the x-axis, and that's like a cubic would. So like a cubic function, so like x cubed. So it means it's either going up and up like that, or it's going down and down like that. So it looks like x cubed, or maybe negative x cubed. So in other words, the multiplicity makes the function look like that particular power function at that particular point. So the summary here, the takeaway. The multiplicity tells you what power function it resembles at that point. And higher even act like multiplicity 2, and higher odd act like multiplicity 3. So higher even means like multiplicity 2, and higher odd means like multiplicity 3. So for example, let's take actually that function f of x equals x minus 1 times x plus 1 squared times x plus 2 cubed, and let's graph this on Desmos. Alright, so we can pull the Desmos back up, and we'll put in the function that we were just talking about, and we'll look at what there is to see about the nature of those different x-intercepts. So the function was x minus 1 times x plus 1 squared times x plus 2 cubed. Now here I've still got the window from the previous function. In order to get a little bit better view of things, I need to occasionally make some adjustments here. Let's make that go negative 20 50 to 20 instead of negative 50 to 50 and see what that looks like. Okay, now let's make actually this more like 10. In fact, let's make it more like maybe 5. And make this more like negative. Yeah, that's probably good. Okay. So notice what we've got here, and this is the way it's going to be, by the way, with Desmos. You're going to need to tinker with the window quite a bit in order to get a good view of the various things that happen. But the important things to look at here are at the three X-intercepts. We have a -1, a -2, and a +1. And at the -1, you can see that what's actually happening, if we were to zoom in just on that one, is that this, if all I saw were that, it would look a lot like x cubed. Alright, so at -2, it looks an awful lot like x cubed. Now, if I were to look just at the -1 and look at that, it looks an awful lot like a square. And then if I move over to here, to this side, to the 1, it's going straight up through, almost vertically, but actually, if you look at it very carefully, you can see it's not quite vertical. It's still got a little bit of a slant. So those are the 3 points that we're talking about here, and they each are doing their own thing as determined by their multiplicity. So we looked at the graph on Desmos, and here we're going to put down the important things about it. However, we're going to exaggerate some things in order to make them easier to see. So at x equals -2, that one had multiplicity 3. And at -2, what we saw was something that looked like a cubic. So it's like a cubic. And then at -1, that one had multiplicity 2. And so here what's happening is it bounces off like a parabola. And then it goes down, and then it goes up very steeply through this point at x equals 1, but it passes through. Passes straight through. Like a line. So that's the important thing about that. Now we have found the multiplicities of the various zeros of this, and if we had something that required a little bit more complicated factoring, we'd use the same techniques we just used before. But now let's turn the tables on something like this and figure out how to find a formula for a polynomial. Finding a formula for a polynomial. So here's what we're going to do. So we're going to be given, for example, a graph, and we're going to use the graph to determine the intercepts and their apparent multiplicities. So use the graph to identify the zeros and their apparent multiplicities. So use these to set up factors with exponents. Then there might be a coefficient in front that we need to settle. So put a coefficient of, and we'll just call it a letter like A, in front. Then use an additional point. Such as, frequently what we'll use is the y-intercept, such as the y-intercept to solve for A. So let's see how this will go. And as an example, we'll just sketch a graph and find its formula. Let's say we had a graph that looked like this. So it goes down, comes up, goes down, hits, and then goes up, like so. And let's say that the points in question here are -1, 1, 2, and let's say that this number here is 16. Alright, so the things that we can already tell about this are you can tell what the zeros are and their apparent multiplicities. So the zeros, x equals -1, and the apparent multiplicity of that, because if you look at it, it bounces off, and if you were to just look at that particular part of the graph, it would look like a parabola. That tells us it's a multiplicity of 2. It's like a degree 2 polynomial. Okay, well then that tells us x plus 1 equals 0, so then x plus 1 will be the factor with a power of 2. X equals 1. Now that one, if we look at that particular value, it's just going straight on through, doesn't even hesitate. So that's going multiplicity 1 like a line, which means x minus 1 equals 0, so just move everything to one side to figure out what the factor is going to be. And then the multiplicity will be the power. So multiplicity of 1 means a power of 1, which we don't typically write. And then over here we'll have x equals 2, multiplicity of 3 because of the way it's just wiggling its way through. And then what that tells you is that you're going to have x minus 2 equals 0, so that's going to be the factor. So it's going to be x minus 2 cubed. So that gives us most of the formula. F of x is equal to, we've got a mystery a times x plus 1 squared times x minus 1 times x minus 2 cubed, but we still need to find the a. And to find the a, what we use is one more point, and that one more point will be 0, comma 16. And the way we use that is 0 is going to play the role of x, 16 is going to play the role of y. So everywhere there is an x, we'll put in a 0, and we'll have 16 as the output. So 16 equals the mystery a times 0 plus 1, 0 minus 1, 0 minus 2 cubed. So if we multiply this all out, we're going to get negative 8 times negative 1 is positive 8. So that's going to be a times 8 equals 16, which if we divide both sides by 8, we'll get a equals 2. So then that gives us the final formula. F of x is equal to 2 times x plus 1 squared, x minus 1, x minus 2 cubed. And a note. Zeros are also sometimes called roots. Okay. Now, as our last task, what we are going to want to do is put the pieces that go into the graph of a polynomial all together to actually sketch the graph of the polynomial. So, graphing polynomials by hand. The idea here is you need to put all the pieces together. So here are the pieces we need to put together. Find the y-intercept. And plot on graph. Find X-intercepts. And multiplicities. And plot on graph. Determine end behavior and put indicating arrows on the graph. Then connect the pieces using multiplicities to determine whether the function goes above or below the x-axis after each 0. And as a hint, I always think it's easier to work from the end behavior inward. All right, let's try an example of this, and an example like the following. Let's go h of x is equal to x plus 1 squared times x minus 3 cubed. Okay, so let's find the y-intercept to start with. So that's where you just plug in 0 for the x and see what you get. It's going to be 1 squared, negative 3 cubed. It's going to equal negative 27. Now for the x-intercepts, those are going to come from the different factors. So x plus 1 squared equals 0 means x plus 1 will equal 0, which means x will equal negative 1. And the multiplicity there will be 2 because that was the exponent. Similarly, x minus 3 cubed equals 0 means x minus 3 has to equal 0, which means x equals 3. And the multiplicity of that will be 3. So this is going to bounce like a parabola. This one is going to wiggle like a cubic. Okay, so those are noted. And then we need to figure out the end behavior. So the end behavior here h of x is going to be approximately equal to, in its leading term, and here you can just discretely forget about all of the lesser degree terms within each factor, just as we said in the previous section. And so that's going to be x squared, x cubed, so that's going to be like x to the 5th, which importantly is going to be negative when x is negative and positive when x is positive. So that means it's going to be down and up. And I don't have to write it with all the infinity stuff for this. I just need to really know the down on the left, up on the right. That's the important thing about this. Okay, let's put all the pieces that we just found into play. Alright, so the y-intercept is negative 27. So I'll say that that's what that is. Other important stuff here, we know x equals 3 is a big number for us. By the way, the x scale and the y scale don't have to be the same. So this can be, so 3 can be that and 27 can be that, and that's fine. Alright, and we know that it is down on the left, we know that it is up on the right. So then our goal is, in a continuous polynomial type way, I have to try to connect the pieces that I know. So I know it's coming from below, then I know it goes to here, and then at this point, because this has multiplicity 2, I know it's going to bounce off. And I know it's going to bounce off, and it's going to go down to here. I don't know exactly how it's going to act in the meantime. This is just all speculation, to be honest. but we know it's going to be going down, then we know it's going to be going up. And we know that this next zero that is approaching has multiplicity of 3, so that means it goes through in a wiggly way. And we have no real way of telling about the how deep it dips right here. None of our business really in some ways, so we won't even worry about it. But the important thing is that we correctly reflect what it's doing at each of the x-intercepts and how it begins and ends, and also what its y-intercept is. Now let's just do one more of these. So let's take something like this. This is, so example, n of x is equal to negative 2x times x plus 1 squared times x minus 2. So first off, we need the easy stuff, such as the y-intercept, which is what you get when you set x equal to 0. So n of 0 is equal to 0 times stuff, but I already lost interest because once I know it's being multiplied by 0, then I know that the overall result is equal to 0. Okay, now for the x-intercepts, along with their multiplicities, we're going to have negative 2x equals 0, which means x equals 0. No exponent, so the multiplicity of 1. X plus 1 squared equals 0, which means x plus 1 equals 0, which means x equals negative 1, multiplicity 2. X minus 2 equals 0 means x equals 2, multiplicity 1. And the end behavior. So for the end behavior here, we are going to just look at the leading terms within each factor. So that's going to be negative 2x, x squared, and an x. So it looks like there's going to be x to the 4th and negative 2 for a coefficient. So negative 2 and then a power of 4. So that means it's going to be, because it's an even power, it's going to be matching left and right. And because it's a negative coefficient, that means they're going to be matching going down. And now, the final phase of this is just to put all the pieces together and make a graph. So now we just make the graph by putting the pieces that we know into play. So we know that 0 is a y-intercept, also an x-intercept. We know that there is another x-intercept at x equals negative 1. We know that there is one at x equals positive 2. We know that it is ending below on both sides, both to the left and to the right. We know this one has a multiplicity of 2. This one has a multiplicity of 1. That one has a multiplicity of 1. So what that means is that as it comes up to this one, it bounces off looking kind of like a parabola. And then it does a little dip, and then goes down and up, and it goes through there, and then it ends up going down that way. Now, we can't tell how high it spikes in the meantime here, we can't tell how low it dips here. All we are responsible for are the specific locations of the things that we can account for. we can account for all of the x-intercepts, and we can account for the y-intercept and the end behavior. Now for the final look here, let's just compare the graphs that we have just made, these two graphs, with what we will see on Desmos. So bear with me for just 1 second here. Okay, so here on the left you see the graphs as we made them, and over here you see Desmos. So I'm going to now put in the formula for the first of the graphs. H of x equals x plus 1 squared and then times x minus 3 cubed. And now, to get a better view of it, I am going to get some of this stuff out of the way, and I'm going to zoom it out a little bit. And notice, actually best if you actually tinker a little bit with it because the scale that comes with Desmos will never quite line up with what you want. So just go a little bit below the earliest x value you want, a little bit after the highest x value that you want. And then we know that went down as far as negative 27 for the y, so we'll go ahead and give it a little bit extra space here, make it negative 35 up to 10, I don't know. And then if we look at that compared with what we had, and actually I'm just gonna move this out ever so slightly more just so that it matches a little bit better. Yeah, there we go. So we look at what we had, what we drew, and what we have here, and it matches pretty nicely. So this one is supposed to go with this one. Not too shabby. Okay, now coming back to the drawing board for the second one. So the second one, the graph was called, the function was called n of x. So I'll keep the names the same just for the sake of consistency. And now delete. All right, so I'll have negative 2x times x plus 1 squared times x minus 2. And that should end up looking like this. Now again, you will typically in these have to make some adjustments to the window to make them look the way you want, but already it's looking pretty good. And if I just make a slight adjustment to my y window, make it go from, let's say, negative 10 to 10, then what we've got here is, again, not perfect compared with what we had, but good enough. Good enough. What we couldn't tell really was how deep this one dipped or how high that one went, but that's not really actually much of our business. The class where you will learn how to do that is actually calculus. So in calculus, you'll learn how to figure out the locations of these top and bottom points, which Desmos here indicates with those, but that's not really our business right now. Our business is these 3 points. Okay, and on that note, let's call that a section. Thank you for joining me for this episode of Math 111. I'll see you on Wednesday.